Okay, so I'm going to do a quick recap on what binary numbers are. This is an anticipation of using the bitwise operators. So firstly, what I'm going to mention to you is that computers use their main constituent component is a transistor. And a transistor can obviously be used as an amplifier and so on, but when it's used for digital and for logic, it's used in two states, on or off. And this can also be called cutoff and saturation. Now the point here is that we can use one of these states, such as the off, we can use as a 0, and we can use the on as a 1. Now that may seem quite limiting when it comes to actually counting numbers, so if we want to do mathematical calculations and so on, but in effect all we have to do is use a lot of transistors in a row in order to come up with any number that we need. The thing is that these will use binary numbers rather than decimal numbers, and so we need to have an idea of how we combine between the two. So what I'm going to do here is I'm going to do up a quick binary table. This is really only a recap. I'm not trying to teach you binary that you'll have to go for. If you haven't come across it before, you really will have to do a little bit more on it than just what I'm going to show you here. But I'm going to do up a quick binary table. So I'll just pause here when I'm building up this table. Okay, so the way to build up one of these binary tables is that we start with 0, then we go to 1, we go back to 0, back to 1, and we repeat this process all the way down this column. In the next column, we do 2 zeros and then 2 1s, 2 zeros and then 2 1s, 2 zeros, 2 1s, 2 zeros, 2 1s. Now, it would be easy to assume in the next one you're going to do 3 zeros, but in fact these go up, these double each time because of the fact that there are two symbols in it. So we go 0, 0, 0, 0, so 4 of them, then 4 1s, then 4 zeros, then 4 1s. And finally, we're going to do 8 zeros and 8 1s. So we double each time. Now, each of these sets here is a binary number, and their equivalent in decimal is as follows: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. However, because of the fact that we can quite easily put these into sets of 4, and that doesn't quite match up with what we do in decimal, we can use another system called hexadecimal. So this one here is decimal. These ones here are binary, so that's all binary. And this one here is hexadecimal. And this works as follows: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I've done that wrong. Immediately I was still doing decimal. So we go, once we get to 9, we have to use a new symbol. So we start with A, B, C, D, E, and F. So these are hexadecimal digits, and what this means is that for any binary number we can split it up into sections of 4 and then turn them into one individual digit here. So it's quite useful for dealing with large sets of binary numbers to be able to change them into hexadecimal, and you'll see that when we come to doing the bitwise operations that I'll actually do a little bit of that. So that's binary, decimal, and hexadecimal. Now, so I'm going to leave that at that. As I say, that's really only just a very quick recap. If you don't know binary and hexadecimal and so on, and being able to convert between the two and that, it's important that that you go and you actually research up on how that works if you haven't ever covered it before yourselves, or if it's if you're very rusty on it, make sure you go back and review it again.